Welcome to the 9th lecture of this course on calculus. Today we are going to learn a very important result, a result of great consequence which can be applied in many places, in many ways, in fact can be used to prove the intermediate value theorem, which shows that how things are actually connected. So, let me write down the theorem, which is an important one, the result. So, I write it as a theorem, which is the way mathematicians express important results, and then we will try to explain each and every part of it. We are not going to completely prove this result, as I said, but show some applications of this, and let me I write it down first and explain it to you. So, let f from AB to R be a continuous function. A continuous function, okay. Then f is bounded on AB and its bounds are at end. We will explain each of these terms separately. So, first we have to talk about what is the meaning of this term bounded. So, we will first discuss what is a bounded set. This is the first step to understanding this result. So, we will take a subset S of R So, S be a subset of R, proper subset by the way, and then we will call S to be bounded if given any x in S. So, or rather I put it in this way that I will call S to be bounded if I can find two numbers capital M and small m, two real numbers, such that whenever I take an x from S, x must be bigger than m or bigger than small m and less than capital M. So, S is said to be bounded if there exists real numbers m, capital M and small m, such that x, whatever x you choose from S, the value of x is always lying between these two real numbers. So, in that sense x is called bounded. Now, there is another way of expressing boundedness. Many people would like to prefer that way, that S is bounded, I am making a short form of bounded BDD, if there exists a positive number say k that is k greater than 0 such that the absolute value of x is strictly less than k. There is no real difference between these two definition of boundedness of a set, because this implies this is same as writing x is lying between k and minus k. So, that is the thing that I want to say, that there is really no major difference. So, whichever way you can use it. I introduced two terms called the maximum and minimum of a function. So, a point y in AB is said to be the maximum of f over AB if f of x is less than equal to f of y for all x in AB. So, sometimes we write this as f of y is equal to the max of f x x element of AB. This is another notational way of writing what we have just written down. So, that goes for the maximum. So, I would expect that you would definitely define the notion of a minimum. So, if you're not sure how to do it, so I just again do it. A point x bar in AB is a minimum of f over AB if f of x bar is less than f of x for all x in AB. So, one is the smallest functional value, one is the largest functional value. So, these things sometimes also written as f of x bar is the minimum value of f of x, where x ranges over A to B. It might look just a symbolical thing, but it has this class of problems are hugely important in optimization and in many practical applications. So, you have this basic idea now written down. So, first, what is meant by f is bounded? So, f is bounded, this term implies that the range of f is bounded. Obviously, you know by now what is the meaning of range of f, and so I am not going to write down what is the meaning of range of f, but f is bounded implies this, and if range of f is bounded, then we say f is bounded. So, this is the link. So, boundedness of a function is linked to the boundedness of a set. So, what is the meaning of being attained? What is the meaning of its bounds are attained? F is said to attain its bounds if there exists y element of AB and x bar element of AB such that Fy is the maximum value in the way we have just defined. And f of x bar is the minimum value that is the meaning of f attaining its bounds. So, basically if you have to prove that f is bounded on AB, then you really have to show that the range is bound in the bounded set in R, and then you have to show that there are points y and x bar for which these are true, and that is the maximizing point, or and x bar is the minimizing point. So, attaining its bound means that there exists an y and x for which this holds. So, these are the maximum and minimum values. So, we will have a better idea of this when we study the notion of supremum and infimum tomorrow in tomorrow's class in lecture 10. So, let me start giving a hint of how such a thing is proved. The key idea behind this whole story is that we have f a to b to be a continuous function. This is a very, very important fact. Without the continuity, your result might fail. So, we will first demonstrate an example and then try to show how the proof of this thing is done. So, I am going to assert that this idea of continuity of the function that is there in the hypothesis is very important. You cannot just say, oh, I do not care, it need not be continuous, every function should have this. No, every function too need not have this. So, let me define this function. Let us look at this function. So, when I say f is bounded, it essentially means f is both bounded above and below. So, this actually means there exists real numbers capital M and small m such that f of x lies between these two numbers, with f of x less than capital M and f of x bigger than small m. This has to be true for every x that you choose in AB. That is essentially the meaning of boundedness. So, if you have this part, but do not have this part, then we call the function is bounded below. If you have this thing to be true, but not this thing, you cannot find any number m for which this is true, then it is said to be bounded above. So, apart from just being bounded, there are two more additional terms which is called bounded above and bounded below. So, these things have to be kept in mind. For example, let us look at this function. This is, as you can immediately in your mind's eye draw the graph. So, this is 1. So, this point is 1 1. Maybe I should draw it. The scale is very bad. Maybe I should have 1 here. So, this is 0, this is 1, and this point is 1 1, and at 0 the value is 1. So, you can understand it is a discontinuous function, but you see the function is bounded below, because here for any x here f of x is bigger than equal to 1. So, you have found your small m, but is there a large m here? No, because all the values of the function. So, here you see my minimum value is attained at this one value, this is the bound. I will show that you see f of 1 is 1 and f of 0 is 1. So, f of 1 is 1 and f of 0 is also 1. So, this is your x bar. So, it is attained, the minimum value is attained. This is bounded below, but it is not bounded above. You cannot find the capital M for this function. The key fact is that you have lost continuity. Losing continuity is a very, very important issue. Losing compactness could be an important issue too, even if continuity is there. I will give you a very straightforward example. One of the most favorite ones is to look at the graph of f x equal to e to the power minus x. I am sure that you have learned something about this number e, a mathematical constant, and its representation through an infinite series, though we will discuss it in more detail. If you e to the power 0 is 1, so if you want to write this thing, then this is like this. So, when you put 0, the functional value is 1. Now, I am looking at the function here, my AB is now whole of R. I am trying to find whether a function defined here from R to R, this is a function from R to R, whether this function is bounded or not. Look at the fact, the range of the function is actually R plus the non-negative real line, non-negative values of y, and non-negative real line is never ever bounded. So, you can see that this function, the value goes down towards 0, it almost touches the x axis, you feel as if it is going to touch the x axis, but it never does so, right. It almost is going to touch 0. So, the minimum value of this, the lower bound, you can say 0 is a lower bound. Here f of x, as you see everything is non-negative, is greater than or equal to 0. So, your small m is 0, but is there an upper bound? The answer is no, because as you keep coming towards the negative side, the functional value will keep on increasing, it will be e to the power some positive number, and then it will just keep on increasing. So, here I have continuity of the function over the whole real line, but I do not have the compactness, this whole line R is not compact. Now, you might ask me that you have given examples, but etc., told a lot of things, but what is this compact business, what does it mean? So, let me explain to these things to you. So, there are two terms, compact, this term compact is a shorthand for a set which has two important properties, closed plus bounded. So, when is a set in the real line closed, and what do you mean by that, right. So, here what we have shown that even if the function is defined over this interval, continuity is done. Here we have defined over whole R. So, basically this, the property of this 0 1 interval is no longer there on the whole R, and thus continuity does not guarantee the existence of the bounds. Here you see there is a lower bound, but there is no x for which this lower bound is attained, there is no x such that f of x is equal to 0 or e to the power minus x equal to 0. So, we know what already is a bounded set which we have told. Compact is a name given to a set which is both bounded and closed. Now, what is a closed set? So, we are going to look at this point. So, before that we look into the nature of a set called open set. So, a set is open, a set or rather a point x element of S is an interior point if there exists delta greater than 0 such that x minus delta, x plus delta, this again is a subset of S. So, such points are called interior points, they are inside. For example, if you take a set like this, say 0 1 open interval, take any point here, do not take these points 1 and 0, take any point here, you can always get a small neighborhood around it. So, and this small neighborhood is inside this set 0 1, inside the open interval 0 1. So, a set is said to be open if all its points are interior points. A set is said to be closed if its complement is open. So, here a set is said to be closed if its complement is open. For example, if I take this interval say a b, of course, it is bounded, every x is lying between a and b, but is it closed? Just look at the exterior part of the other part of the set, the complement, take a point in the complement. You see you can have a small neighborhood around that point which lies in the complement. So, the complement of this set is open. So, this set is closed, and plus it is also bounded, and hence the this closed bounded set. So, an closed interval is a compact set. The real number line is actually both closed and open, because the empty set is assumed to be both closed and open by convention. So, if you take the complement of the real number line, because real number line every point is an interior point, the complement of the real number line, which is phi, is also closed, is as a, you take the real line, then its complement is open, the empty set. So, which means that real line is closed vacuously, in the sense that it is obviously it satisfies all the definition. Now, definition of closedness. So, a set which is said to be closed has as its complement an open set. If a set is said to be closed if its complement is open, and a set is said to be open if its complement is closed. Though you can have this sort of definition for, and they are actually same, you can have this sort of definition that if all its points are interior points, the set is open. So, if you look at the complement of a given set and if you find that all the points are interior points, then the set itself must be closed. But the real line here, for example, in this example is actually closed. The real line is closed, but nevertheless keep in mind that is not bounded. You cannot say that I can give two numbers between which all real numbers lie. This is something you know very well. This is the story of the infinite. So, you really need to take care of these little things. Okay. So, continuity breaking, but set bin compact can lead to problems. Continuity is there of the function, set bin not compact can lead to problems. Now, what we will do, we will try to explain to you why that this result is true, why such a result is actually true. The key idea here is the following. If you take a compact set on a real line, that is a closed and bounded set, and then if you operate a continuous function on it, then the image of that set, right, is also compact. So, take S subset of R and S is compact, and let f be a continuous function from S to R, and f be a continuous function from S to R, then f of S, the image of S under f, the f of S, which is also called the range of S, range of f, that is range of f is compact. So, continuous mapping of a compact set is compact, and that is the whole idea. So, here you can immediately see, since f is continuous, the image f of AB actually is the range of f. So, range of f is compact because the closed interval, as we have seen, is compact. So, the range of f is compact. Range of f is compact, and when the range of f is compact, it is both closed and bounded, and since the range of f is bounded, so there would exist, so range is a set which consists of all. So, what is range of f? A set of all f of x where x is belonging to AB. Now, what would happen? What is the meaning of this being bounded? That there exists small m and capital M such that f of x value lies between these two numbers when x is in the interval AB. That's a key idea. So, essentially then we have proved this fact by using a important result, but we are not going to prove this result. You know, sometimes these theorems which are very important, you can use it in many places, and they should be stated at the very beginning, because that this is one of the key ideas of calculus itself. So, this results needs more ideas, more tools to prove, which we are not doing, of course, because it is a very basic calculus course, though at a slightly higher level. But so here we have proved the first part once we know that. Now, what about the second part? For the second part, we really have to go back to something more fundamental, which is called the supremum and infimum. And that is the topic of the next lecture. So, that would complete 2 weeks of lecture. So, with these very basic facts, today's lecture was very conceptual. It really told you what this theorem means, and this idea can be used in many places. For example, if you know anything, if you know the definition of a polynomial, I do not know how many of you know, but those of you who are ambitious here and who knows the definition of polynomial, if you take a polynomial of even degree on the real line, there would always exist a minimizer. That is, you will always find, you will always be able to prove the existence of a minimizer. So, that is a very interesting fact, but for proving that, you will actually use this idea. That would be given in the notes, as I prepared the notes and gradually put it online, may not be exactly at the same time, but little later. But this is exactly this results, some more application would be shown in the notes, because we have limited time when you were in the class. So, I would rather request you that from tomorrow we are getting into a slightly conceptually higher level. So, before you really look into the lectures from the next one, supremum and infimum, please have a look or relook into the lectures that we have given now. If there is any mistake, if you find something is not fine, you can always write down in your portal and you can always ask the questions to us and we would answer back. My TAs would definitely answer back, and in case even I will also answer back. Thank you very much and all the best.